Am I audible? Just type yes in the chat box if I'm audible. Type yes in the chat box if I'm audible. Okay, good. Good morning, good evening, and good afternoon, all of you from all over the time zones. Let me turn on my video 1 second. Okay, it's already on. Okay. All right. My name is Kunal Ghosh, and I'm the founder of VSD VLSS System Design. This particular webinar, this particular thing that we have planned is especially for all the professors across India and globally. This is also for all the training institutes across the country, and whoever is looking to looking forward to use a lot of AI skills in their semiconductor process. I mean, we have heard a lot about AI is going to replace jobs and AI going to make things. AI is going to automate a lot of things, but how are they exactly going to do it? This is something which we are going to talk about. This is mostly, especially for students, that the things that you've learned till now, it's something that is still needed. But how do you basically, do things on top of what you've already learned using AI, and how do you basically use AI to automate at least 90% of your tasks? And that's what this webinar will be exactly all about. There are live demos. We have arranged for four demos for all of you, and each and every demo will give you a very fundamental idea on how can you use AI for some fundamental applications. That's what you're going to learn today. This is the first ever AI assisted VLSI webinar that we have incorporated in our internship. VSD as a team has worked on a lot of flows that was built using AI, and I think it's been more than 2 years that we've been working on AI assisted flows. And the first time through an internship program, it was basically deployed to all the participants and the students who are going to showcase or demonstrate their work. They're going to show you how did they use AI for their task that was assigned to them. Now, why a student is going to demonstrate to you? Because you will be able to connect to them, because the way they have used AI for their task, you are going to learn a lot from that part. And there will be advanced AI assisted skill, where we are going to the four participants who are going to present their work. Once they complete the 10 weeks of the entire program, you will see some more more crisp usage of AI, more particular usage of AI, and how accurate or how non-accurate it is. We also find out some flaws in which the AI was not actually helpful, and we had to fine tune the prompts in which we have given to get the circuits right and all of this. So this is something which we are going to learn over the next series of webinar. Today, it could be a learning tutorial for all of you on how do you basically use AI. I will be sharing this YouTube link on the on anyways for free. You can just download and check how can you use or apply what you learned today as a part of your your ongoing skills. So it is for all the professors, all the training institutes, and all students across globe who want to start using AI into real design. So we are going to do some real IPs, real designs, and real flows, and you're going to learn how do you basically use AI. It is a fundamental part. How can you use it for your real work? Okay. So it is basically divided into four parts. The first part that we are going to cover is on the SRAM design. So SRAM, so memories, of course, we need memories. Everybody who is doing an embedded system design, or everybody who is doing who are doing building system on chips, you might be aware that memory is where it sits very next to one of the very classic applications of memory is that it sits next to the your processor. The processor basically takes data from the memory. It does the processing and places data back to the memory, and the chip IO port is what is going to take the data from this memory and shift it back to your LEDs and things, and whatever IO ports has been connected. So anyways, that's the application of memory. But how one of the participants, his name is Vijay, and again, the students who are you all of you are going to hear, they are absolute with beginners in this particular field, and the way they have escalated themselves in the last couple of weeks, amazing to see that trend. And hopefully all of you would get inspired on how have they applied their skills, AI skills, on this particular block. Of course, the SRAM template design was already given to them, which was an a VSD IP some time ago. We had built this entire SRAM from scratch a couple of years ago. So we have taken that particular SRAM as a test case, and we have done some AI assisted designs on the same existing test case. So take a look at it, and after that we are going to talk about the mixed signal physical design flow, how AI was used for the mixed signal physical design flow. Okay, so let me start that.
Hello everyone, my name is Vijay Kumar, and as part of the VST internship,
Is it audible, whatever he's saying?
as a track of 4 KB SRAM IP design using AI assistance,
Is it
I am
audible
going
now?
to demonstrate.
Okay, all right, so let's do it.
How AI can effectively assist designers and engineers throughout the verification workflow of the 4 KB SRAM IP. So before we begin, I would like to highlight one important point, that AI is an engineering assistant, not a replacement for a engineering judgment. It can significantly accelerate our understanding of complex circuits, assist in debugging, improve documentation, and also help generated files. So, however, every explanation, every command, results, designs always will be verified using the H4EA tools and their outputs. Ultimately, the designer, the user, the engineer remains responsible for the validating the correctness of the workflow. The main objective of the internship is that not to design the 4 KB SRAM from the scratch. We have been provided a reference repo. I will go through that and I will try to give an overview of the reference repo. This reference repository by Shon Taware contains all the required things for understanding the SRAM IP. So it contains all the post-layout results here. Similarly, pre-layout results are present here. This OpenRAM setup and setup environmented codes are actually present here, the GitHub links and the commands. And coming to the design specifications of the SRAM, 4 KB can also be called as 32 bits 1024 cross 332, which are rows and columns. 1024 denotes the number of rows. 32 denotes the size of the word. The compiler we will be using is OpenRAM, which is especially used for the memories, design of memories, and the process design kit. For this, we will be using Sky 130. The 130 denotes the technological nodes, which we can also say that minimum length of the gate. The lesser will be the technological node, the less will be the power consumption, and higher will be the speed and less uh, area occupation. Right. This are all the table of contents. You can go through this. And again, as I said, these are listed the specifications of the ports and configurations. The operating voltage of the SRAM must be 1.8, right? And the access time is 2.5 nanoseconds. Means the time required to perform the read and write operations after getting the valid control signal and correct address must be less than 2.5 nanoseconds. And again, this should be reminded that Sky 130 a variant will be available after the successful installation of Sky 130. Sky 130 actually contains all the collections of files required to model a fabrication process, like for process design rules, DRS and LVS checkout, and for digital standard cells and input-output libraries, and all the libraries will be present in this. Like you can see GDS files, SPICE files, and tech files, configurable files. And the things we need to know before moving into the actual AI workflow is that we need to give the word size, number of words, and the technology we are using, and the PVT properties like temperature, voltage, and process. We need to give this using a Python configuration to the OpenRAM so that the OpenRAM directly, generates the macros and gives us the final, you know, output like this. It denotes a 2 cross 16 SRAM. This denotes the final 321024 SRAM cell. Now coming to the AI workflow, I tried to understand the project with the help of a codex. The role of OpenRAM and Sky 130 is everything I understood with the help of a codex. The prompt I gave here is that act as a VLSI design engineer, and I gave a reference repository and explain the current scenario. It has given me the entire structure of the repo, and it also provided me a milestone roadmap how I have to go through to understand. And you can see it is given the learning tasks, and coming to the dependency graph, it explains you in a very better manner. Complete the CMOS basics first and go to the 60s cell, understand the read write operations and the SNM concept, and then go to the circuit blocks. It has given me the project check. As you can see that I tried to understand the OpenRAM and Sky 130. So the questions I gave was understand the hierarchical organization of the compiler, the role of this Python wrappers, and the data flow configurations to SRAM generation, and all the key observations and the reusability scalability concepts. As you can see, it not only tried to use one sources, it tried several sources. It has given me the hierarchical organizations, how the Python wrapper is actually converted into every macro, and hierarchical explanation has been given here, and the role of every key files has been also explained at here. And coming to the data flow, it also tried to explain me with the help of a diagram, and model dependency graph, and the reusability scalability concepts, and the investigation notes for the report, and the common misconceptions and the debugs also provided there. And I tried to explore the Sky 130 PDK exploration. For this also I have given the list of questions I wanted to understand, like purpose of Sky 130 PDK, structure of the library files, and how the OpenRAM actually interacts with the Sky 130 technology, abstraction is why important, and what files are required for the SRAM generation I have told you before, and all those things. So not only the reference repo tries to understand with the help of OpenRAM global repo, it has given me the technological hierarchy. What is the purpose of Sky 130 PDK? It explained me with the help of an example like question and answer. What layers actually exist, like metal layers and all, and what devices actually exist in there, and geometrical rules, and the simulation units like models, PVT properties like that, and layout verification rules, and all those things. And also tried to help me with the structure of the folders, and how OpenRAM interacts with Sky 130. Right, this thing we need to understand as well how a configurable Python file is converted into the final GDS, SPICE, and left and lib or Verilog files. And again, it debugs checklist and investigation observations and the common setup and integration issues. Everything has been given it. And the third prompt I used is that how act as a memory design engineer and explain me the operations. Here, I have understood the concepts of everything with the help of this prompt. You can see that read and operation, write operation, hold operation has been explained by the codex in a very well manner. As we know that 60 cell is a two cross coupled CMOS inverter having 6 transistors, and it also known as SRAM. We know the static because of the holding capacity of feedback inverters. And it tried to explain the role of pull up, pull down, NMOS and PMOS, and access NMOS, cross coupling, and everything. See how simply it told you the hold operation, the simplest way, read operation, and it tried to explain you the read path within how hierarchical process has been done. First of all, pre-charge and word line erasers, cell connects to bit line and like that. And write operation also has been explained right here, and pre-charge mechanism and all the circuit mechanism experiments has also been explained right here. and I try to given the refine prompt. As you can see here, it has given me the another important things here. So it also given me the final IEEE format in just like one prompt. As you can see, it also provided me the latex code for the IEEE format. Use ChatGPT to create the prompts for the workflow of week 2 and week 3. It has given me all the prompts, like you can see, the main prompt, and then all prompt 1 to prompt 2. As you can see, it is trying to give you the prompts related to everything. So we will try to execute one of the prompt in Codex, and we will see how it will help in the execution of the circuit blocks. It will take some time to understand the GitHub repository. As you can see, it is still generating the output. With the help of this one master prompt, the Codex has generated everything we need to know about the task 2, like for week 3 and week 3. As you can see, theory, circuit explanation, signal flow, read and write mode, operation, timing, behavior, practical implementation, required file, simulation approach, right? For writing the test benches and simulation, and for read simulation and write simulations, and debugging strategy and expected outputs, and what can be the common mistakes and questions before moving on. So now I will try to give one of the specific prompt related to operation, and I will we will see how it goes. So I will show you the way how I actually generated the schematic and simulation using this flow. So here I'm trying to understand this read operation using Codex. I have used the same flow for drawing the schematic and simulation. I will show you in my repo after a while. As you can see, it is generating the initial states and everything. Address input, what should be the address input, everything. Like I have understood everything with the help of Codex like this, and I will take you to the GitHub repo of mine. As you can see, it will give you a clear clarity of what read operation and object and everything. So you can approach this process for better understanding. These are all the operations I have done with the help of ChatGPT and Codex. I have drawn the schematic, and I got the simulations, and as well as the schematic netlist I have generated from the scheme only. As you can see, the netlist is also present here. And I will show you the errors and the prompts which I have used for the verification of the simulations with the AI assistant flow. So in this, I will show you the errors and how I fix the problems to get the simulations right. So the prompt I have used is this for this workflow, and I tried to perform the wordline driver with this prompt. So initially I got the netlist. You can see this netlist at here. So the error was uh, it was not having models like from Sky 130. It was not integrated with Sky 130. So I have checked the ngSpice version, and I find the Spice Lab of Sky 130, and I have integrated that, and I got the correct path of that, and I fixed that, and I have got the updated netlist at here, and I got the right results. So I have tried for the bitline behavior. The prompt I have updated it because I have used use a verified Sky130 library path, and I have given this prompt. So initially it gave me the netlist which is presented here. You can go through this. And the problem was the previous netlist was it was the bitline capacitance was discharging excessively. I verified with the ngSpice. So I have updated the netlist using the debugging method. As you can see, I have added the PMOS precharge transistors and pre-control signals and all these things. I got the updated netlist at here. As you can see, the simulations are here. Initial simulation output at here, which is discharging excessively, and the updated simulation, this is a perfect simulation, and I verified with the ChatGPT. So coming to the right driver also, AI has helped me to break the things, and it has included the transient analysis also at here, and I did the right path, which according to the user, the path will vary with respect to 1% to 1%. So we need to careful at that point. And coming to the latch regenerative latch verification, it again divided into several stages. So in this AND gate for the decoder macro, I got an error that the voltage sources with if expression in the test bench for the simulation, it was using the if condition. My ngSpice returned that no such function like if, so the simulation was interrupted. So I have understood the root cause and the resolution also. So I've also tried to perform the whole static hold SNM with the same prompt, and I got the results with the Python simulation. Now I will try to explain you the demo. So I'm using Ubuntu WSL for the project implementation. So this is the thing. I will move to the internship track. So inside SRAM Sky 130, the cloned GitHub repo has been there. So as you can see that it contains all those things we have seen in the reference repository. So it has OpenRAM framework, the Sky 130 based SRAM, resources documentation, and my task 2 implementation. So I move to task 2 to explain you this demo. So as you can see, it is divided into schematics and a netlist. This schematic contains all my work related to the scheme, and netlist have the generated netlist present in them. So move to the schematic. So we'll list them. As so now I will try to explain you with the write operation schematic. Xchem write operation dot ch means schematic. Let us see. So as you can see, this is the schematic diagram. So this is the schematic of write operation. Everything I have generated with the help of an AI. These code blocks are very important. You should keep the library path, and this is the code for plotting the waveforms. These are the initial conditions at Q and Q bar. For write, so we can directly generate by clicking the netlist at here. Circuit, I gave the reference image from the repo and asked to give me the best implementation strategy. So as you can see that it has given the identify each transistor sizing and all those things, and how to use the primitive devices, building the CMOS transistor inverter first and cross couple them and add the access transistors. Preserving the transistor sizing is very important, and create proper pins. And it's also given me the wiring overview and suggested the hierarchy first. Then another thing I want is the code blocks code. So for that, it also gave me the library inclusion. We need to verify depending upon our environment, we need to debug that, and the power supply conditions, what line, and the bit line conditions, and the initial conditions of Q and Q bar. Both are different thing. We can go with anyone. And at last, it also given me the whole code, as you can see. So we need to verify these all conditions and generate the schematic. Once the schematic is complete, we should simulate the netlist. So now we go to the, so now we move to netlist, change directly to netlist. So we'll list them. As you can see, write operation spice has been generated at here. So directly try to simulate it with the help of ngSpice. ngSpice write operation. You can also directly simulate it from the Xchem also. Dot spice file. Let's see. It will take some time. This is not a problem. As you can see, it has generated the output. You can also verify this output by taking a screenshot or giving to the ChatGPT, is this behavior is correct or not. I will also try to explain the wordline driver simulation verification. Initially, I gave this prompt to the AI. It has generated me the initial netlist. We can go through this and copy the entire file. And after that, we will use Nano to generate the spice netlist, to edit it actually. So vd1.spice for the wordline driver initial stage. So we can directly copy it here. So after copying it here, you need to save it. So to save it, we need to click Control O and enter, and you can directly quit out of it. So after that, we need to use ngSpice for the simulation dot spice. Let us see. So as you can see that no compatibility mode selected, unknown device type error, simulation interrupted due to error. So I gave this what was the error I gave to the AI and tried to get the new netlist. So the problem was I haven't given the correct library path. As I told, it is very important. We found out the root cause, like to get the actual location, and I have updated the updated the netlist on based on this. So again, we can copy this netlist updated one. This is the updated netlist. If we copy this updated netlist from here, copied. Now again coming to the terminal, I have used a touch to create a spice netlist wd for the second netlist dot spice. Now I'm going to edit it with the help of a nano editor wd dot spice. Now I copy the entire netlist at here, copy paste it. Now we need to save it, Control O. Now enter. Now Control X for exit. Now we do the simulation again for the updated netlist. ngSpice wd do 2.spice. Let's see what it gives. So it will again take some time. As you can see, this has generated the waveform. This is a similar waveform I have in my GitHub repository. So you can follow this approach. So at the end, I want to conclude is that AI will help the engineers for the acceleration, but it cannot replace engineering judgment. So thanks for the internship opportunity which has been provided by Kunal Gosa. This internship is not only strengthened my understanding of SRAM design and verification using OpenRAM and Sky 130 PDK. It also helped me to effectively integrate AI into a real engineering workflow. Thank you once again. Thank you for watching.
All right, good. So this was an initial part where where the AI was used, and
Hello.
hopefully the idea is pretty much clear that AI will not, as he said towards the end, AI is not going to solve all your problems. It is going to at least make sure that 90% of your problems are getting solved, and for remaining 10% is something which you need to use your own intellect and give the right kind of prompts to make sure things actually work in your favor. So it's a kind of thing that you have to use the AI very wisely. So what he shared was a minimal use of AI for the circuit design part, and there are much more complex applications of AI as well in VLSI. In fact, I will share after this call about the entire chip that was it was a mixed signal chip that was completely ported from 130 nanometer technology node to 110 nanometer technology node, through the entire AI flow. It took about in a typical scenario as a chip designer, it would have taken us around 6 to 8 months of work, but with the help of Codex and Claude and all the other AI tools, it takes about, I think, 5 weeks of time that it was taken for us to move an entire chip. I'll share that link of the chip after this particular webinar. So it definitely eases up your task as long as you know the kind of prompts that all of you are asking. But definitely, it is people who are actually using AI. They might replace the jobs of those engineers who are actually not using AI in the day-to-day work. And it has, just like 10 years ago or 15 years ago, Google was a standard way for our search engine. Today, AI is a standard way of doing things. Okay. All right. So, anyways, next one is about mixed signal physical design. So, this is again a very important concept. So what we learned in the previous talk was about a macro. For example, memory that can be called as an IP or a macro. And in this particular webinar, how do you basically integrate? This is a very we are going to take a small example over here, but the concept overall remains same on how do you basically integrate a macro or an IP or an analog IP and connect it via digital design flow. So this particular thing or talk will be about that. Before we introduce how did we use AI for mixed signal physical design. This particular topic will be an introduction to the mixed signal design for anybody in the audience who are not aware of the mixed signal design part or the mixed signal physical design part. This particular lab demo will give you a brief idea about how does the mixed signal design actually works. And these are very important concepts that are being asked as a part of your interviews, and something which again designers need to be aware of if they are working in the area of mixed signal physical design. Physical design is very simple. It's just a simple RTW GTS flow, which you can do using some commands. But mixed signal needs some amount of intelligence. And then after this webinar, after this particular talk, there will be another talk on how two of the participants have actually used AI in the mixed signal design flow as well. Okay, so let's go with the uh, second webinar, second talk. Let me play it over here.
Hello everyone, I am Induvi. In this video, we discuss about the mixed signal VLSI design and a detailed demonstration of mixed signal 2x1 mux. Let's start the theory part. First, what is mixed signal? A single chip that combines the digital logic and analog macro is the mixed signal VLSI. While digital logic is written as the synthesizable RTL code, analog macro is designed at the transistor level, so we cannot synthesize the analog macro. While we can place and route the digital block, we can represent the analog macro as .lib, .lib or .gds file. Why it is needed? Because in this world, everything is an analog signal. Pure digital cannot drive the analog signal, so we combine the analog with the digital to make a single chip for a better performance. These are the some areas use the mixed signal VLSI design. Next, we see about physical design flow. Physical design have the 6 stages. First stage is synthesis. Synthesis is the conversion of RTL code to gate level netlist, like a behavior to gate level netlist. Floor plan. Fix the die area, power plan, like that. Placement. Placement is a placing the cells in the fixed place. CTS is the clock tree synthesis, balance the clock signal, and routing. Routing is the wire, the wiring, all those things. And sign off. Sign off is the verification part. The final GDS doesn't have it verify the final GDS doesn't have any bug. Let's start the detailed demonstration of mixed signal 2x1 mux. Before we start the physical design, we need all the required input file in this directory. So I take a help from the AI. I tell to the Claude, generate all the input files. This is the response. Before we copying all the input files, we need to verify the generated input files.
AI generate all the Verilog files under tickle files, but it could not generate the .lib file under .lib file. So we need to generate the .lib file and .lib file by using the analog magic layout and Verilog 2 lib Perl script. These two files are in a reference repo, so I clone that repo and make use of that.
This is the command to open the technology file under the .magic file. Let's do that. You can see the layout of the analog mux 2.1. It's right the left file. We can see that yes, it generate the lib file. Now we close this. For the lib file, this is the command. We copy this. This is the command to get a .lib file. We need to give the directory. It's yes, .lib file is generated. All the files are generated. Now we copy that to respected directory and start the physical design part. Let's start the physical design of mixed signal 2x1 mux. For that, I go to the OpenLAN container. This is the OpenLAN container and I give a command. This is the command to run the physical design part. This Flora tickle have the tool command to run the physical design. This is the command to run the entire physical design part. I go to the interactive mode. So we can do the physical design step by step. This is the preparation. and all our reports are generated in this path. First, we start with the synthesis. We know synthesis is the conversion of a RTL to gate level netlist. Synthesis completed. You can see the report in this path. Now you can see that. Okay. Yes. It generates the lib file. Now we close this. For the lib file, what is that? This is the command. We copy this. Go to the log file and go to the synthesis. You can see these are the log files that is generated by one log. Open the log file. You can see the IOSIS is running and our RTL is converted into the gate level netlist. You can see that. Yeah, you can see. This is the command to get a .lib file. Our design is converted into the gate level netlist. So now can close this part and this cell. In the result part, in the result directory, the designmux.v file is generated. This is the gate level netlist. Next, we run the floor plan. Yeah. Floor plan part is done. Now you can see that. You can see the deb file here. This is the floor plan deb file. Now we can open the magic to see. This is the text file. The magic is open with the Sky 138 text file. Sorry, Sky 138 technology. Now you can read the you can see this cell could not be read by the magic, so I use this command to read this cell. These cells are in this directory, so that I tell to read this cells. Enter. Now you can do the different. Yeah, you can see this is the floor plan, our floor plan of our DesignMux. This is the input pins, output pins. This is the power grid. This is the cells. Now exit from the magic. Next, we do the placement. Yeah, placement is done. You can see the dep file is created. Now again, sorry. You open the magic with the Sky 130 technology. First, we need to read the lib file and then read the dep file. Now you can see the cells are in the floor plan part, the cells are in this area, but in the placement part, the cells are arranged. Okay, we want to zoom in. This is how the placement is done. Now we do a CTS, clock tree synthesis. If you want to see the reports and outputs, you go to this path and verify your outputs. CTS is running. Yeah, CTS is completed. Now you can check. CTS. Yeah, design mux.def file is created. Now we open in the magic. Yeah, now we can close the routing pause. Now we can check the routing is done or not. You can see the def file is created. Yeah. After the routing, our chip design is like this. You want to see. Next, we generate the GDS file. Sorry. You can see streaming out GDS2 with magic. The magic left file and all those things are written in this path. Go to sign. Yeah. The design mux GDS is written. You want to see that? This is the final GDS after the routing, but we need to verify the DRC check and LBS check before we giving it to the fabrication unit. So for the DRC check, and magic DRC, magic DRC. Now there is 26 violation in the DRC. Oh my god. It's okay. Run the LBS. The GDS2 file have the 26 violation and some LBS error. So we need to fix this to get a final GDS2 file. This is after fixing this error, the final GDS2 file is generated. This is all about after clearing the DRC and the LBS check. The final GDS2 file is generated in this directory. Now I can see that GDS file is generated. Now you can see the layout part. This is the final GDS2 file of our mixed signal 2x1 mux. That's all about the video. Thanking you.
Okay, so if you have noticed,
Hello everyone. Hello everyone.
yeah, so if you have noticed this particular flow and the concept that we were trying to put out over here was that a mixed signal is doesn't need that all the standard cells should be of the same size. It can be of the different variety of heights and variety of functionality. And the idea over here is to how do you basically PNR this kind of block. So that's the whole concept behind this one. But the same thing what Indu just explained overlaps. The same thing, if let's say somebody had to automate it even more with even more features, that's what could be done, and that is what we are going to showcase as a part of the next two talks. It will be done by Arman and Krutika, and again. All this entire work took about 6 to 7 weeks of entire work, which was presented as a 20-minute video. So take a look into now that you understand the physical design flow, now that you understand mixed signal design flow, how do you basically use the AI to generate the configuration files, to generate some of the important files and use them, and how do you not completely rely on AI and make sure that your prompts are quite rightly put. So all these things are something which we are going to talk about in few minutes from now. So let's move on to the next talk by Armand and Krutika, where they are going to talk about how did they use AI in generating the same kind of files and reproducing the same kind of outputs. Okay, so let's begin.
Hello, my name is Moșescu Armand, and this is my video submission for the VSD mixed signal AI assisted workflow internship. Today I'm going to show you how you can replicate this 2x1 multiplexer workflow from the GitHub target repo VSD mixed signal flow. This is basically the place and route of a 2x1 analog IP multiplexer carried out by EDA tools, specifically OpenLane and Magic. And this is going to be an interactive demonstration. I already have Claude here with the model Sonnet 4.6 using medium usage, and because not two workflows are the same, here is my prompt list, but this is my last session, and I'm going to tell it to replicate the entire workflow to go through it. Let's give me a summary of all the terminal commands used and set the flow.tcl. Okay, so first of all, we're going to find all the needed files. There we go. So here we have all the synthesis files, all the lib files, all the leb files, the left files, sorry. Quite a lot. I'm not going to paste this into Claude as it's going to reach the maximum usage. But now we're going to inspect the configuration files. Okay, this is my config file. I'll include it in my GitHub. Sorry. Now, let's see what OpenLay version and Docker we have. Okay, so we have the latest OpenLane version. That's good. Then we'll discover the PDK on the host computer. We have it at Voler. Okay, this was the OpenLane containers. It's an error, but no problem. We'll launch the flow right now. It's a clean launch using the flow.tcl which I built earlier. So let's see. Okay, it already has a run for run fresh, so let's redo that. I'll use random. Okay, let's see. So now it's preparing the left files. It's also doing synthesis, routing, floor placement, STA analysis, parasitic extraction is doing everything. As it's synthesizing, let's analyze the flow.tcl workflow. Let's analyze the flow. Okay, so here is the script. We have the environment block, the pre-flight cleanup using a new container for Docker, for OpenLane, sorry. Then we have the Docker launch. And here in flow.tcl, we have synthesis, floor plan, placement, PDN, routing, RC extraction, static timing analysis, and sign-off, magic, netgen, layout. I'm using magic. Then we'll have a results copy block with the GDS, reports and logs, and the summary printer with DRC, LVS, and antenna. Then here's the environment declaration, but I wanted to showcase the flow that TCL that I built. Okay, the flow is complete. Sky 1.30 black box. This is okay. Sorry. Okay, Docker launch. Okay. I've used the 90% of my session limit. Let's do the remaining to tell it or no, I believe I already gave it that command. Let's go a bit above. I want it to show us the magic layout and also the report. Let's see. Okay, so here we have the manufacturability report, metrics, static timing analysis summary, DRC, GDS location, and finally we'll have magic layout. Let's go. Okay, so now here we have the layout. This is our layout for our implemented analog IP. Here we have it, the multiplexer, and let's see the DRC check, as we have DRC 82 here, but I know for a fact that our DRC is clean, and this is just an importing issue because of the Sky 130 lib. So let's see. I already have here a command. So let's paste it. Okay, the dimensions look all right. Okay, So we have 82 error tiles, but the total DRC errors found is 0. Here we have it explained that the 82 error tiles are Magic's internal highlighting of DRC issues inside the multiplexer subcell. This is mostly this is because Magic doesn't flatten the into black box macros for the DRC. So basically the layout is looking good. Let's go to the manufacturing summary. Here everything is looking quite good as well. We have DRC 0, LVS clean, the number of nets is 6, everything good there. Static timing analysis looks pretty good as well. We have it summarized here. Basically the synthesis is clean, the floor planning is good, placement as well, routing. DRC has 0 violations at the top level, the LVS is clean. And static timing analysis for setup has no violations, for hold no violations as well. The GDS is generated, the CVC and IR drop is skipped because we have no macros, and the VC errors file isn't present. So all in all, this AI assisted workflow turned out quite alright. I'll include the updated prompt list on my GitHub, and see you soon. Thank you.
Hello, I'm Kritika and this is my demonstration video for the VSD Mixed Signal AI Workflow Internship. In this video, I'm going to show you the step-by-step how I used AI tools, specifically ChatGPT and OpenAI Codex to assist in the circuit design work for a mixed signal flow. Everything I demonstrate here can be reproduced by anyone with the required tools and PDKs already installed. Let me give you a quick overview of the project. The reference repository I'm working with is the VSD Mixed Signal Flow by Prahasha. The link is over here. It demonstrates how an analog hard macro called AMUX 2:1 analog multiplexer is integrated with digital SPI control logic using OpenLane on the Sky 130 process design kit. The circuit block I selected is this AMUX macro. It sits at the boundary between the analog and the digital domains in this design. My design goal was to use AI to analyze this repository, generate real design files like the OpenLane configuration and the Verilog black box wrapper, simulate the design, validate the outputs, and also document everything. The expected result is a set of verified AI generated design artifacts that can be used as part of a real mixed signal implementation flow. Now let me switch to my GitHub code space and show you the entire workflow live. I'm now in CodeSpace. This is a browser-based VS Code environment connected directly to my repository. I've already cloned the reference repository, which I just showed. Now I ran the tree minus L3 command to show the complete folder structure of the reference repository. As you can see, the repository contains several important sections. Here under the Verilog folder, these are the RTL source files. Design mux is the top level module. The AMUX is the analog macro, the Raven underscore spy, and the spy slave are the digital SPI logic. Under left The AMUX left file is a physical abstraction of the analog macro that OpenLane uses for placement and routing. Under lib, the timing model for the macro is present, and under OpenLane, the configuration file config.tcl and the automation script.tcl are present. So now I'll be looking at the top level RTL to understand the design. This is the top level Verilog file, that is the design underscore mux. You can see it instantiates two submodules. The AMUX is the analog multiplexer as a hard macro, and the Raven underscore SPI, which contains the digital SPI controller. This is the mixed signal boundary. The digital logic controls the analog multiplexer through the select signal. And this is the OpenLane automation script. It runs the full flow, that is the synthesis, flow plan, placement, routing, DRC, and the layout generation, all from a single script. The add lefts command near the top is what integrates the analog macro into the digital flow using its left abstraction. I'm using Codex here. I've given it a very specific prompt that includes the design name, the PDK, the analog macro name, the clock port, and the clock period. The more specific your prompt, the better the output. So Codex has generated a complete config.tcl file. You can see it's defined all the key parameters. Design name is set to design underscore mux. Verilog files point to the RTL sources. The Verilog underscore files underscore black box points to the analog macro black box definition. The extra underscore lefts integrates the physical abstraction, and the clock meters are set to SCK at 10 nanoseconds. Each parameter is explained in the comments. Now let me switch back to the code space and show you the actual generated files I saved from this process. Here is the config.tcl file I generated and saved during the project. You can see it matches with what Codex just produced. This file is what would be used to run the OpenLane physical design flow for this mixed signal design. Now let me show you the left file for the AMUX macro. This is the physical abstraction that OpenLane uses. You can see it defines the macro dimensions 8.740 by 5.440 microns, and the pin definitions for select, IO. So there's I0, I1, out, VDD, and VSS over here. It also includes routing geometry and antenna information. I used AI to analyze this file and generate an engineering report. Let me show you that next. I'm giving Codex the key parts of the left file and asking it to explain what each section means from a physical design perspective. Now you can see Codex has explained the macro dimensions, the pin functions, and most importantly, how the left abstraction allows OpenLane to place and route this analog macro without needing to know its internal transistor level implementation. This is exactly how mixed signal integration works. I'll show you how I used AI to generate the Verilog black box wrapper for the AMAX macro. This file is critical. It's what tells the synthesis tool to treat this analog block as a hard macro and not try to synthesize it. Notice how I'm specifying the exact pin names from the left file. Uh, Over here, consistency between the Verilog wrapper, the left and the lip files is absolutely critical in a mixed signal flow. If any pin name doesn't match, the physical design tool will fail to connect them correctly. So Codex has generated the black box wrapper. The key things to notice are the black box attribute at the top, which tells the synthesis tool to preserve this instance. The port list matches the left pin names exactly, and the module name is completely empty. There is no behavioral implementation at all. The actual analog behavior usually happens in the silicon and not in the simulation. So this is the file I generated and saved. It matches exactly what the codex just produced. So now this is the validation step. This is where I compared the AI generated configuration against the reference repository's actual configuration to catch any mistakes. Now look at the clock port parameter over here. This is my AI generated file. Codex set the clock port to STK, which makes intuitive sense since this is an SPI design. But when I check the reference repository's config, it actually uses select as the clock port. This is a real error that would have caused issues in the physical design flow. The AI made a reasonable assumption, but it was wrong. This is exactly why manual verification is always necessary after AI generation. So all of these errors I found are documented in the experiment 9 in my GitHub repository. All the errors are documented over here. So these are the physical design outputs from the reference repository. These are the final results of a completed OpenLane run. The design underscore mux.gds is the final chip layout in the GDS format. The design underscore mux dot left is the abstract layout for the completed design, and design underscore mux dot mag is the magic layout file. These files confirm that the mixed signal flow integrating the AMAX analog macro with the digital SPI logic completed successfully end to end. I'll be running the workflow in my GitHub code space. the OpenLane outputs to my GitHub repo over here. Since GitHub cannot render GDS files directly, it appears as a view raw in the repository. I verified the layout by opening the GDS inLedit, which I'll be showing now. The final GDS layout in theLedit. Here you can see the top level cell design mux, and on the left side the AMUX macro is also present in the imported layout database. This confirms that the final mixed signal layout was generated and that the analog macro was integrated into the top level design. So to summarize, I successfully recreated the mixed signal OpenLane flow, resolved synthesis and macro integration, placement, PDN and routing issues, and generated the final design MUX GDS layout containing the AMUX analog macro. So this is my final output. So to summarize what this video demonstrated, using ChatGPT and Codex, I generated a complete OpenLane configuration file, a Verilog black box wrapper for the analog macro, and also an left engineering analysis, all from natural language prompts. I also identified real errors in the AI generated outputs, particularly the wrong clock port. The key takeaway is that AI can dramatically accelerates design exploration and artifact generation, but manual verification remains essential. Every AI generated file in this project was validated before acceptance. All prompts, generated files, commands, screenshots, and observations are documented in my GitHub repository, and yeah, you can have a look at it. Thank you.
Okay, so that was the final one.
Hello.
Yeah, so that was the final demo for all of you. Now, what you saw over here was a very fundamental application of AI, which I'm sure all of you must have taken a note, and you can actually use those in as a part of your current workflow. Maybe you can try it out because these are all available openly on GitHub, so you can try it out and see how the different results are something which you get, and compare those results with what others are getting. Anyone who is a little bit aware of the LLM models, he or she can easily identify that if you have one base repo or a base system created with a predefined LLM, there could be a way where you can actually the exact prompts will work on a standard LLM which you can create and deploy on a GPU or a cloud CPU, and it will give you some prediction in the result. So that's also possible if somebody wants to build an entire AI tool chain specifically for the VLSI front. That's always possible. Second thing, if you want to, there is a website called as Hugging Face, where you can find all the LLM models. You can take up any fundamental one. It will take, of course, a lot of GPU and CPU. Yeah, either you can do it on cloud or you can buy a separate GPU. But there is a way that you can deploy a small LLM into your own machine and create a VLSI stack only specific to VLSI stack. That's all possible. Something which we are also taking a look at, so that in future we can give you a standard cloud GPU interface like on DigitalOcean, and maybe you can try out some of the VLSI specific LLM models or VLSI specific AI tasks on those GPUs. So that's something which is a work in progress, and this, I would say, this is just the beginning. All of you have a long way to go, and before we wrap up everything, it's time for Q&A. So anybody, so if you have any questions, this is the right time to ask. Let me unmute participants over here. If you want, you can basically unmute and ask your queries. Okay, so a couple of questions came in the Zoom chat box. Let me try to address those. 1 second. So I have completed my training in VLSI and Kate and Switch tool. So this one is open source tool OpenLane. You can take a look at the GitHub repository. Which nanometer? So this is 130 nanometers, and okay, this was a couple of questions by now. Okay, all right. Anybody has any queries? You can unmute and ask all the queries. This is a good time to stay in. When we started our work with VSD, and from there there was not even a good online platform back there in 2010 when I graduated from masters. I graduated from IIT Bombay, and at that time there was not even a good online platform to talk about things. But now we have all of it, and we should definitely take lot more advantage. So if I have taken 4 years to prepare for a VLSI field, it should trim down to a years of preparation, at least 12 months of preparation for the current generation. So we are at very good times. Things are going at a very faster pace. But what we learned 5 years or 4 years before, or even 3 years before, that somewhere is not much more. That flow itself is not much more valid because that part is basically taken care or automated by AI. Something that we are looking forward for is how do you use AI or assist AI or use AI assisted flows in your current VLSI program. So that is what we are going forward for. If anybody has any questions, there is a question on YouTube. What is the vision and mission of VSD? Yeah, you can watch the website. All the updates are there on the website. The entire mission and vision statement. You can find it on our website. And could we know whether open source PTKs could work and fabric in India? In SCL Mohali, they have released a 1.2 micron PDKs, which could be used for some fundamental prototyping purposes. Because if you look into the physics part of it, 1.2 microns channel length are quite bigger, and the short channel effects are not very visible in a 1.2 micron channel length compared to if you shrink to 180 or anything below 250 nanometers. The short channel effects comes into picture, and that impacts overall your standard cell design, your timing, and all of it it's getting impacted. So today with the open source SCL Mohali, sorry, somebody has to mute. Okay, today with the open source flow, I think they are targeting 1.2 micron flow, 1.2 micron PDK. I think it should be released in this month or so. Once we have those PDKs, we are going to build flows around it. We're going to build flows around the 1.2 micron for only for the study purposes. For production, I'm not sure anybody would be using 1.2 micron because things today are moving at about 1 gigahertz, at least above 500 megahertz, and 1.2 micron might not give you that kind of speed that we expect for today's kind of application. But yeah, it's a good learning resource. From where can we access tools? You can access it on. There are a lot of links. If you search for OpenLane, I think you get all the tools online. You can access it online. It's all available. Already, yeah. Anybody has any? There was one more question by whom? Okay, no, this was just a personal message sent by somebody. Okay, anybody has any more questions? And there are some more webinars coming up. We are going to talk about. There will be a webinar on FPGA, how you build IPs for RISC-V IPs for FPGA. There will be a webinar on an Edge AI. How do you basically deploy Edge AI models on the board? So there will be a webinar on that as well. There's a question: is it possible for us to get SL Mohali PDK for Synopsys? Actually, we are aiming to project on C2S, but unfortunately, we don't have. So this is something I'm not sure. The C2S and CDAC how that part actually operates. What I understand is you need to contact the nearest C2S and CDAC for the PDKs. But I don't know, because VSD, it's a private entity, and we don't channelize work between SL and CDAC. We use their their collaterals for our work under an MOU, but we do not form a bridge between them and us. So, or maybe just drop me a message. I need to understand clearly what is happening. So maybe I could guide you better. Okay. Okay. Anybody else? Any more questions? Vijay Kumar, open source Kaivanti. Yeah, it is open source Kaivanti PDK. I don't know whether that was a question or that was by reply by Vijay. Okay. All right. So if there are no more questions, we do something called as a photo session. All of you turn on your cameras and we'll do this V, and we'll take a quick snapshot of this particular webinar. So yeah, all of you turn on your cameras and do this V for victory in front of the cameras, and we'll take a quick photo and we'll wrap this webinar. All right. Okay, quickly, anybody, everybody. Quickly turn on your cameras and we'll do this photo session. Oh, sorry. It is disabled. 1 second. Yeah, you can actually start. You can actually open up your cameras now. We'll do this V in front of the camera. All right, good. All of you. Can someone take a photo? Because I think, okay, let me also try to take, if I'm able to take a photo. Yeah, Ankit, can you take a photo? Can you take a quick pic? Ankit, if you have joined. Or Dhanvanti, if you have joined, can you take a quick photo?
Just a second, I'm doing.
Yeah. All right, ready?
Just a second.
Okay. Done? Okay, yeah, I think I have taken one photo here. All right, thanks all of you. Thanks for joining, and I'll share the. I think it's on YouTube also. It'll be quickly be live on YouTube, and you can take the link and maybe you can check out how can you use the flows that was explained today on your own designs. Okay, and if you have any queries, anything, just drop me a message on the WhatsApp group. You can just send me a message on the WhatsApp, and we would love to help you out. Okay, thanks all of you. Thanks for joining. Bye.